Okay, so I guess we can start. So my name is Tomek Kogut, that's my Twitter handle, if any one of you want to contact me afterwards. What I'm going to tell you about today, so the topic of presentation is Bestiary of FP with cats. So if any one of you doesn't know what Bestiary is, so Bestiary is a type of book that especially popular in Middle Ages that would list all the beasts, mythical one and non-mythical ones. So that may, like, at least to some extent explain why we're talking about beasts in FP, because there are a lot of different terms that are not understandable at first sight. Okay, so short info about me. So I'm a software data engineer in Adform. We're working on developing a platform for ads. I'm working in the research department, working on supply forecasting. I don't want to bore you with info about me, so last information is I'm doing Scala since about 2011. Okay, let's go to the content. Oh yeah, I forgot, we're hiring. Okay, so first a warning. So some of the information in this presentation, I wanted the presentation to be a very practical guide, intro to FP and CAT. But some information may be inaccurate, and that is on purpose, because I don't want to mix up different things that might blur the image. At the same time, some of the information might be plain wrong, and this is because I'm no expert. I don't have a PhD in category theory, so I apologize here for that. And the last note is that if you have any questions during the presentation, it would be very nice if you would ask them, so it would let me to understand the needs of you. Okay, so why this talk? So I, and probably maybe a lot of you who did some FP, feel that FP is kind of a different beast. It doesn't resemble anything that you might have contact with. And reading blog posts and short information about FP actually doesn't help a lot. I think it's even more frustrating that you read a blog post about something, somebody shows you something, yeah, it's so cool, and then you sit down, you work, and okay, so how do I attach that monad to my code base? JPA proxy adapter factory something, right? And yeah, and let's forget it. Let's do a for loop. So the thing that everyone needs to understand is that this is completely different from everything you know, because most of the programmers start with doing imperative programming, so with those for loops and etc. And FP is more like math. So there are some strange definition at the beginning that doesn't make a lot of sense. Then you do some exercises, right? Like in math classes. And then some things start to tick, right? Then you okay, I think I got it. And then you go deeper and deeper, and everybody says that you're a lunatic, right? Because you're talking about math. So yeah, this presentation is my try on how to take a deep dive into the FP world. I went through some of the hoops that are daunting, and I hope you wouldn't need to if you will try. Okay, so from your perspective, so functional programming, what is all about? What? Value. I hate you. Oh, functions. Thanks. Yeah, functions. That's the first thing that will come to my mind. I will kill you afterwards. Yeah, functions. Something else? And you don't say composition. Yeah, composition also. Okay, so you said almost all of the things then, but in different orders. So yeah, so few things that may come to your mind are functions, utility, statelessness, and things like that. Higher order function, if somebody heard about those. And if we try to, I don't know, take them all together and somehow fit, I believe that actually functional programming is about values. That's why I'm going to kill you. So why values? And what are those values actually? So values are whatever you want. Those might be bits, ints, data structures, functions, or even types. And the most important thing is how you will combine those things, because this is the essence of functional programming. So you'll take different values and combine them and create new ones that will serve you. And this is actually what we'll be doing through all the presentation, showing how to combine different values. Okay, so let's get to the real content. The first time that you might encounter going into functional programming, a very simple one, in cats and everything, you will see something called a product. So a product is actually like you take two things, put them in one box, and you treat as one. So you have a class foo, a class bar, and then you have a product of them that holds them both. Nothing very special in this. The same thing serves the tuples, and sometimes you can meet with a term Cartesian product, let's say in the cat's code base. Okay, first thing, easy, nothing to spend time on. The second thing that you will probably encounter is a semigroup. So semigroup is about taking two values and combining them together to produce a one value. So let's try to define semigroup interface in Scala. So we have a trait, semigroup. We try to not be concrete, so we created it as a generic one. So it is expressed in the terms of A, that will be defined later. And here we got the method definition, combine. So you will take one A, second A, and return an A from it. Nothing very unusual. So a short note. Now you can ask me, so okay, why this is called a semigroup? Why don't you call it like values combine or something? So FP is based a lot of math, a lot of algebraic structures, and a lot of research that was put into it. And people can use some of the laws that the mathematicians developed and apply them to the code. I don't want to talk about those laws today. You can check them out on Wikipedia. This is actually a copy-paste from this site. And I'm not going to focus on this because I think this will blur the overall image. But there will be a lot of those strange names that you might have encountered if you were somewhere in the university. Yeah?
Monad is which of them?
Actually, I think none. Actually, I think Monad is somewhere else. Like I said, I'm not a PhD from category theory, and I'm more of a practitioner.
Monad is a monoid in category of Functors.
Yeah, let's don't repeat that too much. Okay, so how do you use that semigroup in your code? So let's say a short thing. Does everybody knows this syntax in Scala? Somebody doesn't know it? Okay, cool. So I don't have to tell. So we have a superadder. We're creating a superadder that will add things. So we say that we can take two things and we can add them if, that's our condition, if the A has a type class semigroup available. If it has, we take that semigroup A, combine those two values. So how do you apply it to your real code? So let's say you have a case class complex number and you want to use the superadder to add two complex numbers. So you need to provide the semigroup from complex number. That's pretty easy, right? You just need to add the equivalent positions, and that's mostly it. And you can use it. You can use superadder on ints. You can use superadder now on complex numbers. You can use the superadder on strings. Why and strings and ints before we provided semigroup? That's because cats provided it, but we'll get to that later. Okay, so now one might ask, so we have a semigroup for int, so int is pretty like a simple thing. What about some more complicated stuff, like for example list, options, or futures? There are like more variables and have other things that you can put inside. So let's say you would try to create a semigroup for option. What would happen? So the Scala compiler would complain that the class option takes type parameters, and you cannot create this one. Well, we could take a shortcut. We could create a semigroup for option of int, but this is not something that would please us because, well, we said that option is from int. What about options of strings and options of everything other? So this is something that won't work for us. So we can do better. And to get to how to do that, we need to first think about exactly what is option list and future and stuff like that. Because they seem like a normal types, but they actually something that is called constructor for types or higher kinded types. So what they do is if you have an option, you need to put in another type inside to get a proper type. So you can read that those types have holes inside. And funny thing, well, actually, since I think Scala 2.11 or 2.10, I think 2.11 is actually knows about those types. So if you go to Scala rep and ask for the kind of string, the rep will say, so Java-lang string kind is A, it will say an asterisk, and this is a proper type. Let's look at some other types. For example, what is option that we've been talking about? So kind of option is F plus A, and something like this. And this is a type constructor, a first ordered kind type. This is exactly what you would say in Scala rep. So now let's think for a second. So let's omit the plus sign. This is about variance. We're not talking about variance today. So does this resemble something to you? Something, arrow, something.
Function.
Yeah, exactly. This is a function. And this is actually used in Haskell to denote how how high is the order of the type, sorry. So as I said, option before you put a proper type inside is a type constructor. Option of int is something called a proper type. So this is actually, so option is actually a function that takes types as arguments. Let's look at some other types. So we got kind of either. So either's kind is f a1, a2. Does this resemble something from Scala? Like you have an argument and you have an argument in another part of parentheses. Carrying, yeah, this is actually carrying. This is carrying for types. So first you put in an A1 and you have a partial application of that type. Then you will do that type 2, the second type, and you'll have a proper type. Okay, so now for the scary part. Because that was easy, right? What about types that take types as types inside types? So what is the kind of trait foo that takes an x and that x takes something as an argument also? So foo kind is x, f, a. And this? Does this resemble something? So what actually is this? The first part.
Function parameter.
Yeah, so this is not a parameter for a type parameter, this is a function parameter. So the first thing you need to put inside foo is something that serves as a function. So this is x, because x also needs a type inside. So you need a type inside a type to have a type. That's this whole story with this. So we have the theory now. Let's go to the practical part. So we want to create something that's called a SemigroupK, and SemigroupK will not accept a single a parameter. It will accept a function that a type that is a function that will take another type. And that too, we have a combined k that will take 2f a. I will just say a in the context of f, okay, to be clear. And now let's create a semigroup for option based on SemigroupK. So we do a combine on option a and option a, and we return option a. And we just do f a1 or else f a2. Like, we didn't need to specify anything about a. Like, we don't care about a. We only care about option. And you can see that a is non-existent in here. Right? So you don't need to pass it nowhere. Here you got the same definition but for lists. And then you can use those. So actually you saw that there was a semigroup and there was a semigroup K. So something K is actually very common in cats. So K stands for kind. So if you have some type in cats that, for example, like semigroup, and you have a field that you need to pass not a proper type but a higher order kind type, so you'll need to look for something with the K suffix. So our effects will work on higher kinder types. So in cats you will find SemigroupK, Monoid K, function K, all around the code base. Okay. So you don't need to actually provide a definition of semigroup because we got cats. I just wanted to show you how it's actually like defined underneath. For all the standard types, you actually have all the instances for. You don't need to write semigroup for list, option, etc. for future because they're already there. You only need to import things. So if you want to use semigroup in your code base, you just do an import cats and import cat implicits, and you can summon a semigroup for int, and you have a combine method there. You have a SemigroupK for list. You can combine those, etc. A quick question: what is this? I mean, and syntactically, how this is defined? Again, look at the code. How would you define this in Scala?
Short type.
No. I mean, what is this? This is what? Sorry?
Probably it's a trait.
Because why can you do a dot combine? So what is this?
Object.
Yeah, object. But like, how is defined? Like, have you seen anywhere in your code like?
It's an implicit value, probably. So you can pull it out of thin air because it's in the context. Cats implicits must contain a value that has implicit value that has this type, right?
Like normally you would say implicitly semigroup, right?
Oh yeah.
So this is something different. Well, actually, this is very, very easy. But the first, like,
Yeah.
this thing is something that you see for the first time. It actually is like obvious. But then you start to think, how do I write this? And you don't know. And this is actually very easy. So this is actually object semigroup that has an apply method, but without the first pair of parentheses. It has an implicit on the first parameter, and it just like takes the implicit and returns it. So it works exactly the same implicitly in Scala, but like it has a nicer syntax, I think. And this is taken from the cats library exactly. Okay, and this is also something that is very common in cats. So you got a type constructor, like here, semigroup. You will say for which type you want it, and you will then invoke some method on it. And this involves heavy use of implicit and package objects, so consider compilation time to be non-trivial. Okay, so how all this works underneath, under the hood. So when you import cats, you actually import all of those classes like semigroups, monoids, and etc. And when you import cats implicits, you put all the implicits in the scope, all of them. So this also might be something that is trouble. So how this is implemented? So Cats authors actually did like I would say a trick. So there is this object implicit that extends something called syntax, all syntax, and instances, all instances. So you could use it easily in your code base. But those two things looks like a big mess. So when you're doing those two simple inputs, you're actually importing everything inside. As you can see, we got list instances here that allowed us to, and semigroup syntax here. And this is how the instances looks like. So you have a list instances, and we got that this actually extends a few of those types. And you probably, if you're looking for semigroup, you yeah.
About the previous slide.
Yeah.
Does IntelliJ will manage to optimize those import?
You mean will it remove them? Because the biggest problem with implicit was up till some time that it would remove implicit that are needed. For example, the spray, right? so it won't remove them. It actually will catch them. It won't remove them. But there are some things that won't work flawlessly. Especially that there is some code generating beneath. So, but we'll get to that. But I will be honest, working with cats in IntelliJ is non-trivial. So, yeah, but I stopped in using IntelliJ, so. Yeah, so this is from the cats library list instances. So if you would try to look for example, if you're exploring the code, you're looking, okay, so I have a semigroup, I look for the semigroup instance of list. You go to the list instances and there is no semigroup. Why? Because there is something called monad combine, and monad combine is actually also an alternative, and alternative is a monoid K, and monoid K is semigroup K. So because you have monad combine, you also have a semigroup K operations. I know it is a bit like a bit of mess, but this is actually not because the authors are lunatics, but because of the fragility of Scala language, because there are some problems how to actually implement those things. Okay, so there was this thing also called syntax. So you don't always need to summon those objects. You can do something like this if you have those imports. Why? Because your type will be lifted into something that is called semigroup ops that will have two new operations. So this is normal Scala, like having implicit conversion with additional methods on it. So nothing very unusual. So again, if you have those inputs, you don't need to do a semigroup for something and then combine. You can just call like a method instance. Okay, so we're done with the semigroup. Let's go to another thing. So another thing is something called monoid and monoid K. You already know what K is, so that's good. So monoid is actually a semigroup. Sorry, a semigroup with empty element, and the same for monoid K, right? So what is this, you might ask? So, and this also partially answers your question about IntelliJ. So there is a project called Simulacrum. If you attach a type class annotation to your trait, it will generate some code for you. Like, you know how type classes works in Scala, right? And you can write type classes. Well, I know at least 3 ways how to write type classes in Scala, and this will do it like in the same way always. So the whole code base is looks the same. So jump to source my network. Okay, so more on monoid. So examples of monoid. For example, if you put into monoid an int. So the operation might be a plus, and the empty element is 0, because monoid, the empty element is something that won't change the first argument to the combine. So if the operation is multiply, then it's int. If it's string, then combine is a concatenation of strings, and the empty element is an empty string. Okay, nothing very daunting and problematic, but let's say you start to try to write some code based on cat's code base, and then you want to write a monoid because there is a need for something like that. So let's try to create a monoid for a non-empty list, because one might ask, is it always possible to create those semigroups, monoids, and etc. for every type? So the shortest definition of a non-empty list I know is actually a tuple of an element and a list that might be empty, right? This is clear. Okay, so let's try to write a monoid for non-empty list. So combine is pretty easy, right? And what would be the empty element of non-empty list? Like, empty element is an element that you will add to the non-empty list and you will get the same. So what would be that? Any idea? No. What? But non-empty list is another type, right? This is a non-empty list. So, like, this is pretty usual.
Single element?
Yeah. What?
Single element?
But the type won't match, right? Single element will be A, and non-empty list is this, and single element is this, right? So yeah, that happens a lot. So you may up writing some kind of type class that you actually cannot implement it, and that happened to me like a year ago. And it took me 2 hours to realize that you cannot have an empty element for monoid. So I set a question on Stack Overflow at like 10:37. Like at 12:31, I already responded myself with the answer. So yeah, you cannot do that. So let's look at an example that actually you can create a monoid. This is a pretty artificial example, but I found it somewhere on the internet and it's a bit funny. So let's say that you want to create an ordering, some classes for ordering. So this is pretty obvious way how you would encode it in Scala, right? So you get a trait ordering, you get greater than, less than, equals. And then you have an ordering monoid. So there's the definition that an empty element is equals, and the combine works if you get two orderings, if the first one is equals, then check the second one. If the first one is less than, then don't look at the second one. It's just the answer is less than. The same for greater than. Okay, so this looks really artificial. So how can be this used? So an example. So let's say you want to compare two strings, but you want to have a multiple conditions. Like you want to compare two strings that you want to have that the first string is less than if it's palindrome, and the second way you want to compare a string is that shorter first should be like smaller, right? So what can you do? So you can take list of those functions that you want to actually use as conditions. You can map them, filling them with the arguments. So the rest type is actually a list of this, right? And then you can do a fold on the result of this application. So what fold does, it works the same as fold left that you know from the list in Scala, but it takes an ordering monoid as a second argument. So what will actually happen? So let's look at step by step. So we get two words, Anna and Barbara, and the first comparison is palindrome first, right? So although Anna would be less than Barbara, when you're using the condition palindrome first, it would be greater than, right? Is it clear? Or yeah? In the second comparison, Anna would be less than Barbara. So we have a list of greater than, less than. And then you do a fold, right? And how this fold will behave. So all arguments in that list will be taken and they will be combined. So because the first argument was greater than, then all of the rest arguments are not checked. If the first check would give you equals, like the monoid will go further and check all the other arguments. Since we're like talking about folds, because probably most of you used it in I don't know, list or vector or something. So there is also something called foldable in cats and in overall FP. So the foldable does what you might expect. Yeah, you want to say something? No? What you might expect that it does, it actually takes on your collection and reduces it to a single element, and it's very much connected to the monoid instance you will create, because it will use those monoid instances to actually reduce the collection. And the foldable has all all the elements that you would expect on it, like I mean all the collections API methods, like find, exist for all, filter is empty, etc. So this is like I think all of you like saw fold left or something. So I wanted to show you another combinator called fold map. So fold map, what it does, it actually takes some, like it doesn't say that it's a collection, but it's most useful on collections. For example, list of A. You pass in a function that will map from A to B. So it will somehow change the type. And then it accepts an implicit monoid on the second parameter, and it is a basic fold left, starting with the empty value of B as an accumulator, as an initial element, and it combines both. So how could you use that? So, like example for real life, let's say you got some like an invoice, and you got line items in that invoice, and you want to have a total sum of all the elements. So you just need to call foldable list, fold map on line items, and just change the line item to its value. And it will use the implicit monoid from the scope to actually to sum the values. And alternative version without summoning the foldable list is like using the syntax ops. So if you have those cats imports, you already have fold map in your scope. Okay, next one. So functors. So there's not much to tell about functors. So functors are actually, like they give you a map function. And that's pretty much it. The same as you have on all the types, like an option, on list, or anything. So functor will have a map. On first argument, on first argument you will pass in some context, and a function that will change the value inside that context to some other value, just like here, right? Interesting thing about functors is that they compose, and you can hear a lot about those, that something composes in functional programming and something doesn't compose. And this is something that like is very, like it's hard to understand. So what does it mean that something composes? So like the very basic understanding of compose is that you can actually summon a few functors, call compose on them, and you can have a map that will dig into the most depth type and do the mapping on functions. So like normally if you would have a try of list of option to actually map the type inside down there at the bottom, you would need to do a multiple maps, right? And here you can just do something like this. So you get this special composed functor from try list option. You do a map. You just pass in the function that works on the most depth type. The funny thing is actually notice that we haven't like specified that this will work on ints. The thing that this works on ints is encoded here. So this is also a very abstract type. And here's the result from the rep, that it actually works. Okay, so I want to apologize for this slide, anyone who knows these things, but I wanted to everyone be on the same page, because Scala has this funky the methods of defining functions. So I wanted just to outline them and show one thing that will be needed further to understand something. So probably most of you know something like this, right? So this is a definition of, I don't know, adding to ints. Probably you could see that in the fold left when you would want to reduce a list and add all the elements, right? So you can write a syntax like this. Let's try to push the type parameters from the variable to the method definition. So you can meet something like this. So this is another way. Now let's try to think how would it look like if the first argument would be actually a function. Like I mean, the type here of this underscore wouldn't be an int, but a function of something. So this is so P is actually something that takes a function at the first argument, and an argument and a value and a second argument, and returns int. And this is how it works. Okay? And now, again, let's try to take those types to the left side. How would it look like? So this would be the actual definition of this function. So it looks kind of bizarre, but like I will need this in a few moments, so keep that in mind. Okay? Okay, so applicatives. So applicatives are actually something that if you try to go into code base and read the applicative code, is something that will learn you the most in the beginning. Because all the functions that we've been talking about, like those combine and I don't know, filter and stuff like that, they are called combinators. And in most cases, you just need a very few functions, like let's say 2 of them, and you can create a whole lot of functions out of those 2. And applicatives are about this. So applicative is something that we create because we wanted to have a map function, but for functions of this shape. So not a map that will take a single function for mapping, but a map that will take a 2-argument function. So here it is. So applicative is basically something that has a map2 function that will take 2 arguments and a function of 2 arguments. So exactly what we needed. So this is like almost the same as functor, right? But instead of taking like list and then mapping a list inside, we can take, for example, a list of ints, a list of strings, and do something with the elements of it. And the second method that you would have on the applicatives is called unit, and unit actually takes a value and will lift that value into f. So if applicative will work on lists, if applicative will work on lists, so unit will create a list of that value. The same for option future, yeah?
This is not what I see in the Appidocs.
You mean in the cat's Appidocs?
Yeah.
Remember the warning at the beginning that some things may be inaccurate on purpose?
On purpose?
On purpose, yeah, you could check the Runar book, and I think this was taken from his book.
Right. Yeah, because
yeah, no,
there's pure instead of unit, and AP instead of...
Yeah, don't. Yeah, no, we'll get into that.
Right.
Okay, so applicative is this. So what this actually gives us, because like I haven't given you any value before, but let's try to like create more functions, more on applicative. So let's get some stuff for free. So if we have those 2 functions, we can create some other functions only using those 2. The first one would be a map. So you remember when I told you that there is something called a functor, and functor needs to have a map function, right? So if you have an applicative and you already define those 2 functions, you can also define a single map. And from this, you can say that every applicative is a functor because it has the needed methods. So if you have those 2 methods defined by you for some type, then you will get map for free using only map2. That's the first thing you will get for free. Second, let's say you want to have products of some values. Let's say you got a 1 list, a second list, and you want a tuple of elements, right? So the product is giving you for free because you already defined map2, and this is the definition, and that's all. A lift is something that somebody I think called Pimp My API. So what lift does is if you have some kind of function from A to B, and you want it to have a function from FA to FB. So an example, let's say you're working with some legacy code base and you're working with an API that accepts nulls and return nulls, right? So this might be a null and this might be a null. So you will pass in your legacy function into this. If you have an applicative that works on options, that function will not take A, it will take option of A and return option of B. And that's how you will get rid of nulls. For example, you can get rid of nulls in JDBC that way. You can have a pretty decent API then.
Will cats do that for us?
Uh,
Those three things, for example.
you mean the lift?
And the map and the product, if I define an applicative.
Applicative is already defined in cats. And as I said, you have instances of those things in cats, so you don't need to write them.
But for my own type. If I
For your own type.
Yeah.
For my own
For your
type.
own for your own type.
Applicative,
Yeah.
the map to and unit, will I get map product lift?
Exactly. Exactly. You need to provide those two functions for your own type, and then you will get all of those for free.
Okay.
Traverse. So traverse is best understand if you know future sequence. Traverse is actually like a more abstract thing that sequence. So it takes a list of some values A, takes a function from A to some context F, and it will return of list of B in F. So the example is sequence. If that is very common. You have a list of futures, right? For example, you had to call 10 APIs, so you have 10 futures, but you actually want to have one future. So traverse will take this list of futures and change it to a future that has a list inside with all the results. If somebody doesn't grasp, you have a just think that F is a future, right? So you have a list of values, of arguments. You have a function that goes from that argument to some future with some value inside. So you would have a lot of futures, right? And instead, this will give you one future with a list of results inside. Okay, so we saw that you can have a map 2. Why not to have a map 3? So yeah, this is exactly why I wanted you to remember that part with those method definitions, because this looks very creepy, right? But actually, this is not something very, like, if you go to your editor and try to write it down yourself, that is actually the way that this is how you can understand how it works. I think there's no other way. You just need to try to write map 3 in terms of those two functions, and this will be like an eye-opener. So I don't know if you know what Kogut is. So Kogut is built into Scala. So if you have a function, you can call Kogut on it, and all the arguments will be Kogut, right? And again, curring is not something that is magic. You can write your own curring function, of course, for defined types. So if you have a function from A, B to C, you can have a function from A to B to C, defined like this. So I don't want to get too much with the details how this works, because it's best to go with the editor yourself and try to write it down. Just remember that actually this is like taking a function which was on the first argument and applying the argument of the second position to that function. That helps a lot when you first read the code base. But even if you don't understand actually how this works, you can notice some kind of symmetry in this, right? That there's a FA map 2 something inside this strange pair of parentheses, then FB again map 2 this strange thing, again map 2 FC. So we try to extract this part. So this is something that we could possibly extract, and you will get a function like this. This is something that you want to ruffle.
Yep.
So
that's how it's defined in cats. Map is defined in terms of.
Yeah. So I think that's the biggest problem of the blog post I've read. So if you go to a first blog post about applicatives, you will get, so an applicative is something that has a unit method, that one that you saw before, and an apply. I don't know, if you are able to understand how applicative works from the definition of this, then you're good, really. Like they say that you have a function, like say they show you applicative of list, and they say you got a list of functions. Why do I want a list of functions, you say? So I think like how to understand applicative. So applicative is actually something that gives you those maps 2, maps 3, and etc. So you need maps for like more arguments.
The question is if those lists are of equal length.
Sorry?
The question is if those lists are of equal lengths, the list of functions and the list.
Ah, yeah, that's also true. Okay, so let's try to use that apply to extract some things. Now it looks more like, okay, it's still a bit. It's better. Okay, let's settle on that. It's better. Okay, so using this, we can try to define those like higher maps, like map 4, map 5, etc. Because it's easier to create those in terms of apply. So the funny thing in applicative is that you saw that I had a map 2, right? So I had a map 2 and I created an apply method for my own sake, right? So it turns out that you can create an applicative not giving it map 2 but giving it apply instead. Those two functions can be defined in terms of the other. You can start with the apply and use map2 to define it, or you can start with map2 and define it using apply. So if you want to have it applicated for your own type, whatever is more convenient to you. If you want to define map2, then go ahead. If not, you can use apply. Okay, so real usage of applicative, because like this was like a hardcore theory without any examples. So for example, you were working on some web application and you want to display a chart of best-selling books, music, and games on your web page. You have endpoints, maybe some kind of REST endpoints or something. One way or another, you have 3 methods that return future of sequence of those books, albums, games, etc. So you can do give me an applicative for future, because we're working on future. Map 3, because we have 3 of those. You put inside those futures, and you get the combining function here, and it will put those arguments inside. Another use case for applicative, if you would be reading about something, is a validation. It's actually a good one because it's easy to understand. So if you want to go and dig up and read about applicative, try to find something about validation. And it's also easy to write, actually. Funny thing is, if you would try to write your own validation, I think you would probably end up with something more or less similar to applicative. Really. Okay, more things from cats with applicatives. So this import gives you something that is called, I don't know, I think that's called a scream operator or a rows operator, whatever.
I guess scream is the one.
Scream is the one. Yeah, okay. So you will get this operator, and you can use it, and like this will be implicitly treated as applicative. The difference is that you need to call map here. You didn't have to here. And again, this is something that one would look like first time looking at it. This is obvious. When you start to think about it, how do you think this actually works? That you can, like, because if I would just invoke top books, the scream operator top music, then I would have to put a 2-argument function here, right? To the map. If I have a third thing that I'm combining with this operator, then I have 3 arguments here, right? If I would have a 4th one here, it would be 4th one here. So if you would try to define something like this in Scala, well, I don't think you would manage to. Because, like I said, this is something that you believe that it's obvious. Actually, beneath is implemented with code generators. So that's why, again, something you cannot jump to a definition in IntelliJ in cats in some places, because this is a very high overview of how this works. So there is something called a Cartesian builder. So and actually there are multiple Cartesian builders. There's Cartesian builder 1, 2, 3, 4, up to 22, I guess. So how it works? So if you take a argument, use this, then and pass another something that has an applicative, you will get a Cartesian builder n plus 1. And the map function will take a mapping function one order higher. So for example, if you would have only those two combined, you would have a Cartesian builder 1. From this, you have a Cartesian builder 2, accepting function 2, etc. with the higher levels.
A question.
Yeah.
How is this related to macros, those generators?
How this is
How those generators relates to macros?
I think they do not relate, because I saw in some Scala, I remember there was this big string in some Scala source code that was actually a template that was actually filled like this. You would have a s before the string and interpolation of strings. Nothing else. And this was somehow like written down to disk and compiled without any macros or anything. You would have a step in the build pipeline that would actually create source files. So nothing very, I don't know, magic or anything, right?
If it works, what's the problem?
Yeah. Okay, so let's go further. So again, applicatives also compose. So if you have some type that is like more complex, like for example, you have an option inside a future, no problem. You can create multiple applicatives, compose them, and use them like this. And you wouldn't need to like dig down deeper. Okay, so the beloved monads. I don't want to talk too much about them because, like most of you writing Scala code, use them every day when you call map and flat map. So you probably know how monads works. They are pretty powerful, but they're also pretty restricting because they put certain ordering of computations on you. But let's don't get too deep into that. I would like to show you how you can use monads in your code. So this is something that you might write not once. So you have a DB repo that has a method getUserLogin that accepts an ID. And on the first argument, I want the f, that the DB repo would be parameterized, to be a monad. And we turn f of string. Don't look at the implementation, I just wrote it down so it would compile. You have a second method getUserEmail. And again, it returns f of string. And in the end, you get user that actually use those two methods to combine them. As I said, f is a monad, right? So on f, you get flat map and map, just the way how you would normally combine. And the good thing about this, we said that f is a monad, but we didn't say what kind of monad explicitly. So if you would put here future, then DB repo would return future. If you would put it here an option, then all the methods will return options. And it also works with the more convenient for loop, for comprehension. So yeah, so this is like, for example, a way how to turn your DB repo from asynchronous one to synchronous one. First, you will put a future inside, and in the second implementation, you'll have a try. And that's pretty it. And well, something that again you will hear a lot: monads do not combine. Then you start to think, what does it mean that something combines or not? So basically, what does it mean that monads don't combine? If you have one monad, because list is a monad because of the flatted map inside, and you get another monad inside, you cannot do a for comprehension. This won't work, right? you cannot add I plus j. You can do something like this if you really want, but I would say this is pretty ugly, right? Or you can use cats and write something like this. And we're using something that's called monad transformers. So you need to pack the thing that you have into something called a monad transformer. So you would have a lot of them. So you would have a type and t at the end. And this means that this is probably a monad transformer. So if you see something like this, option t, or whatever t, then just think that this is the type option packed inside some monad. In this case, option is packed inside list. And this will work. So in cats you will find actually multiple things of those, multiple instances of those, like either t, idt, option t, state t, writer t. So how you need to just read those? So we have a something t. So this will be wrapped into this, and this will have inside this. And you don't need to, I don't know, dig inside the type to do the for comprehension like here. Okay, we're heading to an end. I hope you're still with me. Okay, another thing that I could mention is effectful functions. So an effectful function is a function from A to B in some context, and those functions are actually more common than one might think. You actually create a lot of those when writing Scala code. So get customer by ID is actually an effectful function. It's from long to future of customer. Find first in is a function from char sequence to option of string. List from 0 to n is from int to list of int. So there are a lot of those. You use them every day. And the whole presentation was about combining stuff, right? So since we use those functions a lot, we would like to have an opportunity to combine them somehow easily. Yeah, so we want to combine those. So there is something called Kleisli. So Kleisli is actually something that allows us to combine those functions easily. So Kleisli just takes this function as an argument, and it gives you a map and flat map. So you can do the normal for comprehension on those functions. There will be an example in a few moments. Like, I don't want to go through all of this code because like it wouldn't bring us any value. Maybe one thing is that you can meet some kind of like strange functions called with a letter ending. So, well, normally flat map for Kleisli should be of this form, right? Because you need to return on the return time a Kleisli. Well, since we're working on this kind of functions, if it's more convenient, then you will find some functions called the same as those popular ones, but with ending of some f or something like that. Yeah, so Kleisli has all the good combinators that you would want, like map, compose, apply, and all of those combinators will work on this. Yeah, I don't want to get too much into those points. Let's see how actually Kleisli works. So basically, if you work on simple functions, like you have a to b, you can call it and then on that, combine it with b to c, and you have a to c, right? But if you have these effectful functions like a to f of b, and then b to f of c, this won't work. But you can pack it in Kleisli, and this will work. So there is actually a lot more of those types in cats. So you get XOR, that's something like try. You get a state type, validated type. There are free monads and free applicatives, show, traverse, a lot of those. So actually, if you go through the whole presentation, you will know how to read the code, because the things that I shown will be familiar in those types. Okay, so there are a lot of definitions, a lot of funky stuff during the presentation. Let's try to build something with the newly gained knowledge. Let's create a simple RPC system that will be focused on HTTP, and we'll use all the, maybe not all the building blocks, but at least some of them. Okay, so let's try to define what would be a service. So our service, our RPC service, would be a Kleisli future AB. So what is actually Kleisli? So don't mind the Kleisli. So this is a function from A to future B, right? Kleisli is here only for the helpful combinators. So this is our service. So our service is of type from something to future of something. So let's be more concrete. You want a HTTP service. So it will be request to future response, right? Simple. We'll probably need to read some body from the responses or from the requests. So we'll need a type called decoded result of T, because like we want the body to be parsed as objects, right? And now you see either T, future, decoded failure T, doesn't make sense. Then you try to remember that. So either T, this is a monad transformer. What does it mean that's a monad transformer? That either will be put in some kind of monad. Which monad? In future. So a decoded result is actually an either inside a future, and that either returns a decoded failure if we failed, or a T if we succeeded. Okay, then we need something then we need a function that would, this will actually be used only for the DSL. I will show you that in a minute. So we will take a function from A to future B and return a service. So this, and all we need to do is pack the function into Kleisli. So our HTTP service will be actually a partial function, because we'll only respond to some of the requests with responses. Then for the DSL, we don't want to make our client of our library to write future everywhere. We want to allow him to pass in request to response. So we create a function called live to async. So what it does, it actually executes this function asynchronously. So we we take a partial function from request to response. So partial function is of this kind, right? We lift it so that the response would be returned asynchronously, and then we lift it to the service type. And that's how you can use it. You get a partial function from request to some kind of response. Of course, all the plumbing down there, like all the HTTP things, you would need to use some kind of library, for example, I don't know, netty or whatever. But as for DSL, there's a library called HTTP4S, and the definition of HTTP service is actually like this. It's exactly like this. Okay, the funny thing is that we defined a server instance, but we can use the same type to define a client. Because like a client also is, like if you use any kind of HTTP client in Scala, it's always request to future response, right? So let's say you get a HTTP client that is of this type. So remember, this is a function from a wrap function into Kleisli, etc. But essentially, this is response to future, request to future of response. So we can take this HTTP client and do a map on it, because the HTTP service packed our function into Kleisli. So that's why we have the map function. And we can say that, okay, so this is the response, right? Kleisli takes care of wrapping down there, so to remove the future. So this is a response, and we say that we want the response as a JSON body. How this function is defined, this will be shown in another slide. So how to use this function? So we just need to supply it with the request, right? Make a get to the root. And this will automatically have a type of future decoded result of JSON. So how would we implement the client? So we would need some kind of plumbing again, like this time you could use, for example, a AHC client, async HTTP client. So we would wrap the async HTTP client into our own class that would extend request to future auth response. That's the usual apply function, right? We would call the async HTTP client here. So our HTTP client will actually be, the definition of it would be like this. So we pack our wrapper into Kleisli to get all those maps, flat maps, and etc. And we supply the client wrapper with the plumbing. And the coding. So how would this work? So as you saw, that we did something like this. That we had I said this was a response, and we called a method body on it, and we put inside the type JSON. So this is exactly the same trick as I asked you at the beginning. What's SemigroupK, right? So it uses implicits here. So the body of response actually looks for an entity decoder, and it returns decode result, and it decodes itself. And again, so you can look at this, that this is wrapped into Kleisli, but you need to actually look at it as a function from request to future JSON that has this additional map, flat map, and etc. because of the Kleisli. And how the entity decoder would be implemented? So you would have the decode, right, message. This would be like per instance. And you could add a map function. Why? Because if you actually, let's say that you implemented the passing of the binary data, right, to a text. Oh, sorry. If you implemented parsing of the binary data to a text, then there is a lot of things that are based on text. So JSON is based on text, XML is based on text, right? So you could actually go and use the map from binary to text and from text to JSON. And again, the decoded result type is either T, so it's actually either wrapped in future that has our result or decode failure. Okay, so as I said, if you would go from the binary to text, so let's say we got an entity decoder for string, right? We got this decode message that decodes the message and returns our string. This is a dummy implementation, of course. So if we have an entity decoder for string, and then I added a map function for the entity decoder, then we can use that map. And if we have a library that takes strings and can turn those into JSON, so you can do just on the string instance of decoder a map and map the text to a JSON. And you could do the same thing on XML or whatever you could turn string into. Okay. Yeah, and this is how you would probably implement the JSON stuff. Okay, so this is actually everything that I wanted to tell about today. So the takeaways, yeah, this stuff is really hard to actually dig deep into it. To be honest, it's actually probably one of the hardest presentation also for me to give. well, there is no shortcut. You need to spend a lot of time. The only thing you just need to do is go and try to write an applicative yourself. Start with a map to and unite and try to write apply or something. If you have a chance to get this red book, I don't know, from Runar, Functional Programming in Scala, that's an excellent introduction to those topics. It actually goes through all the steps and it will help you to understand this. Like, not everyone will appreciate this style of coding, because I think that the community is divided 90 to 10. Like 90 people would want Scala to be a better Java, and the 10% want Scala to be a lesser Haskell. Yeah, so I'm not saying that you should use it, but knowing this actually like widens your horizons, and you can better understand the code you write, and you can like somehow write a better code even without all the applicatives and stuff like that. Yeah, okay. Thank you. Maybe questions or something. No?
I can add one remark. I recommend studying CAT sources. I was looking at the sources as you were talking, and they are really easy to follow. Compared to Scala Z, it's like 10 times easier. So.
Yeah.
And there's also these Scala exercises, right? With cats as well, nice.
Yeah, they are. Yeah, but I think that you will get the most out of this if you really will try to write all those type classes yourself. That's actually
that's the hard way, no?
Yeah, that's the hard way, but that's also what you do when you try to follow all the exercises from that red book, right?
Mm.
You will go through all the combinators. Okay, so thanks.
Well done.